Okay, so good morning, and today we are going to talk about inheritance in object-oriented programming and in C++. So what is inheritance for? So one of the goals of every object-oriented programming is to reuse software. Okay, so to make the reuse of software as simple as possible. Okay. Now there are two ways of doing this in an object-oriented programming. The first one is called composition, and the second one is called inheritance. Composition means that basically we define an object inside another object and we use it for some reason, or that one object invokes the services of another object by using some reference on some pointer. Okay, so composition is simply one object uses another object. Inheritance instead means I take something existing and I turn this existing class into another one, okay, by adding new and more specific code. So inheritance is a sort of transformation of something that is already existing in something else, while a composition is just one object uses another one. So typically inheritance is represented by, in general, object-oriented programming is represented using UML diagrams. And so this is the classical UML diagram of a class inheritance. So on top you see what is called the base class, is class A. And on bottom you see what is called the derived class. And in this example, B is deriving from A. So basically B extends A, or if you want, B is a more specific version of A. Okay. So typically in this kind of graphical syntax we represent with minus private members, and with dash with the hash symbol we represent protected members, and with plus symbol we represent public members. Okay, so in this case I'm saying that class A has a private integer data member and a protected one, J, and two public functions, get and f. Okay, and class B is a more specialized version of A and has a private member I and two public functions, get and g. And so B derives publicly from A. It means basically that B inherits the interface of A. So first of all, B is a more specific object with respect to A. So this means that first of all, when we construct an object of type B, we must first construct an object of type A and then add the new things. In that case, B, since B derives from A, first of all, when constructing B, first of all we have to construct A, and then we have to initialize the internal member I. Okay, and of course when we do the destruction it will be the other way around. First B is going to be destructed and then A. Okay, and then we define two functions, set and g. Set is going to modify j and I, but you don't see any j in this class. So where is this j coming from? Well, j is coming from class A. In fact, if we go back and look at the declaration of class A, it declares two data members I and j. So when in B, in function set, we refer to j, we are actually referring to the data member declared inside A. Okay, J can be accessed because it has been declared as protected. So protected members can be accessed from derived class, while private members cannot. Also, look at this use of data member I. So we have two variables I here, one defined inside class A, that is private, another one defined inside class B, which is also private. So inside class A, when we say I, for example in function get, we're actually referring to the I declared inside class A. Instead, when we say I inside class B, we are actually referring to the proper internal member I inside class B. Okay, so the scope is based on which class we are using. Okay, so I is a member of B. There is another I that is private member of A, so it cannot be accessed from B. Okay, so whenever now we can use B as a special version of A. That means that basically when declaring a member, an object B of type B, what we do is that we can use all the functions declared inside class A and all the functions declared inside class B, which are private. Which are public, sorry. So basically here in the second line, cout bget, we can use get, and remember the definition, get has been defined inside class A. Okay. So basically what happens is that B inherits all the interface of A, so all the functions, the public members and the public function of A are also used by B. Okay, so let's look at the example now. Okay, so this is class A, which is a base class, and we have constructor and destructor, initialization of the members. Then we have three functions, get, set, and f. And then I have class B, which is a public of A, and I define the constructor, the destructor, a function set, and a function g. So the public interface of B consists of its own functions, set g, and the function inherited by A. So basically get, set, and f. Okay. Notice that set is redefined inside B in a completely different way, and we will see in a while what this means. So in the main, I declare an object of type B, and I call get. And as I said, if we go up and look at the interface of B, there is no get. So what we really mean is to invoke the get of class A. Okay. Then I do set of G of B, and then I call G. Okay, and I call G again. Okay, here and there. Then I define a pointer to an object of class A, and I assign it the address of the object B. And this is possible, and this is called upcasting. So basically this means that I can have a pointer to a base class which points to an object of a derived class, and this is of course possible. Okay. What is not possible to do is the other way around. I cannot have a pointer of B to B which points to an object of the base class. Okay, and this is an error, and if you want to do that, you have to force the casting, but we will see that in a few minutes. Okay, and so this type of casting is perfectly legal. It's called upcasting, and also this of course is perfectly legal. Okay, and also this is perfectly legal. Okay, so let's see what this is going to print. So this prints A, B, 0, 10, and so on. So why it prints A and B? So here I'm invoking the constructor of class B. The constructor of class B first calls the constructor of class A. The constructor of class A prints A with the parentheses here. Then the constructor of B is executed and it prints B here. Okay? So this shows you that for constructing an object of type B, first I have to call the constructor of class A, and then the constructor of class B is called. Okay? This call here is explicit. However, if I don't specify it, it's going to happen anyway, because the compiler is going to insert 1 for sure. So if I delete this, this is still working without any problem, and it's doing exactly the same thing. Of course, if I specify for example an integer parameter here, okay, then of course I'm going to receive an error because there is no default constructor to call here, and so the compiler doesn't know what to pass, and it will give you an error. So when I'm trying to compile, I get an error. Okay? It's trying to call the default constructor, doesn't find one. Okay? Okay, then we have a few printings here and there, and then we go out. So let's continue our analysis. So public inheritance. So in the front of this declaration of the function, you see the word public. And this means actually there are other ways of doing inheritance. There is the so-called private inheritance, and there is protected inheritance. So right now let's concentrate on public inheritance. So you are forced to write public here if you want public inheritance. So public inheritance means that the derived class inherits the same interface of the base class. So all the members in the public part of A became part of the public part of B. And all members in the protected part of A become part of the protected part of B. And finally, all members in the private part of A will not be accessible from B. So private actually means private in the sense that nobody is going to touch it except myself. Protected means, okay, me and my sons, okay, the derived classes can access it. And public means everywhere, everyone. Okay? There is no overloading across classes. Okay? So in particular, if you define f in class A of type which takes an int and a double, and you define f in class B which just takes a double, okay, what happens is that the second f hides the first one. So in the main, if you call bf2 3.0, it will give you an error because it doesn't see any f with two parameters here. It just sees the second f. So AF has been hidden by BF. Okay? To get AF into scope, you have to use the using directive. So basically inside B, you have to use this writing, using AF int and double. Okay? So in our example, we have a function set, which takes two parameters here. And the same function with the same name is also defined into B. Okay, so if I try here to call b set 1, 2, then the compiler will give me an error. Okay? No matching function for calling b set int int. The only candidate is this one. If I want to actually have the set of A into B, what I have to do is to write so now A set is into scope. Sorry, I just forgot. Okay, so I forgot how to write it. Sorry, the here is not very precise, so I'm going to see how to write it and I will tell you later. Okay, so this is just an error, a syntax error. So there is another way of writing it, but I don't remember right now. Okay, so maybe it's just this. I just do a last try. Okay, so yes. So now it's working. So the actual writing is like this. Okay, so this means just use a function set coming from A. You don't need to repeat the prototype. Okay. So as I said, it is possible to use an object of the derived class through a pointer to the base class, and this is called upcasting. So I have a pointer to the base class, and the pointer now points to an object of the derived class. And so when I call pf, that calls a function of the interface of the base class, and that's correct. However, this is going to be an error. So what I have here is a pointer p which points to an object which is of type b. However, the pointer is a pointer to an object of type A. So the compiler in this exact point doesn't know what P is pointing to. So he has no way to know that P is pointing to an object of type B, and so it doesn't know anything about the interface of B. So this one is going to be an error. In other words, what you have to do is to look at the interface of the type of the pointer. P is a pointer to A, and in the interface of A we have a function f. So this call is correct. However, in the interface of A there is no function g, and so this call is an error. Okay? So even if P is pointing to an object of type B, the compiler doesn't know anything about it. The only thing it knows is that P is of type A. And so this one is going to be an error. You can do the same thing that you do with pointers also with the references. So basically here we have a class A and a class B like before, and a function h which takes a reference to an object of type A. Well, what happens is that you can actually pass to h an object of type B. And what happens is that this reference is actually referencing to object. Okay? So like before, it is possible to call functions in the interface of the base class, so of A, and this one is going to be an error because at this point I have no way to understand what kind of real object is X referring to. Okay. So why extending by inheritance is useful? Well, the real use of inheritance is exactly in this piece of code. So when you have a function that works on references or pointers to base classes, I want to make sure that this one is also working on derived classes. So all functions that take a reference or a pointer to A as a parameter continue to be valid and work correctly when we pass a reference or a pointer to B. This means that we can reuse all the code that has been written for A also for B. In particular, all the code that uses references or pointers to A is going to work very well when we pass an object of type B instead of passing object of type A. So you can reuse all the code that is valid for A also for B. And of course, you can also extend the existing class to implement a new functionality by adding new functions to B. Okay? So again, what I can reuse here is, of course, the code inside A. But most importantly, also, I can reuse a function H. So class A and function H, they go together, a part of the same bundle. And then I can extend this by writing a class B, which extends the functionality of A, and I can reuse function H without any problem also on object of type B. Okay? Okay. But what about modifying? So not only extend, but also change the implementation and the behavior of existing code without actually rewriting it. So for doing that, we need the concept of virtual function. So virtual functions are probably very well known to Java programmers and to Python programmers and in general to programmers of dynamic languages, because in object-oriented programming languages like Java, where everything is more dynamic, basically all functions are virtual. In C++ instead, you have this difference between the normal functions and virtual functions. So C++ is more flexible because it gives you the possibility to choose which kind of mechanisms you want to implement. If you want to implement the virtual call, dynamic binding, or you want to implement normal calls with static binding. Okay? So I'm going to give you the typical examples of object-oriented programming languages for introducing the concept of virtual functions. So suppose that you have a program in which you are going to draw shapes. For example, you want to write a program that lets children design simple geometric shapes on the screen. Okay? So you need internally to keep track of the objects that have been designed, and for example, when the windows is moved across the screen, you need to redraw all the shapes. Okay, so one typical way of doing this is to put some common code in a basic class called shape. This is going to be the base class, and then write specific implementation in the derived classes. So you have a more general class, the base class called shape, where, for example, I define the coordinates of the center of the shape, and these are x and y. Okay, and then I define derived classes like circles, which is going to have a radius r, a rectangle, which I'm going to define the length of the two sides, and triangle. Okay, again I define base and the width and the height of the triangle. Okay, and this is, for example, a possible implementation of shape. Okay, and I have class circle, class rectangle, class triangle. And so now let's make an array of shapes, because as I said, the user is going to produce new shapes as the program goes on, and at some point I need to draw all these shapes on the screen. So one thing I could do is to have an array of pointers to shape. And then I'm going to initialize this array by creating objects of type circle, or type rectangle, or type triangle. And this is possible because basically I'm doing upcasting here. So shapes 0 is a pointer to the base class shape and contains the address of an object of a derived class circle. So this is upcasting. Okay? And then I do a for cycle in which I just call the draw function on all the shapes, and I just define the draw function into shape. Okay? Now, which draw function is going to be called? Okay? So if I don't say anything strange, so if I use the normal function call of C++, the function that is going to be called is the one defined inside the base class shape, because as I said before, the compiler doesn't know the actual type of object that is being pointed. Okay? It knows that this is a pointer to a type shape, and so if I don't say anything special, the compiler is going to call the draw function in the generic class shape. However, this is not what I want. What I would like to have is that the specific draw function for the specific classes is going to be called. Okay? Now, for doing this, C++ allows you to put the keyword virtual in front of the function declaration. And what this actually means is that the compiler should not call the draw function defined inside class shape, but it should call the draw function defined in the actual object the pointer points to. So basically here, instead of looking simply at the interface of shape and calling the function inside shape, I'm going to look at the specific type of object that in that moment is being pointed by this pointer, and I'm going to call the corresponding draw function. Now this means that the actual function to be called is not decided at compile time, but it's decided at runtime. So it's decided dynamically. Why? Because in this moment, when the compiler tries to translate this code into actual assembler code, it doesn't know anything about which object is going to be pointed. So it doesn't know which function must be called. Only at runtime, I actually know which function is going to be called. Okay? So what I do is, let's consider a slightly more complex example in which the class shape has more functions. So the class shape has x and y, which are the center of the shape, then a move function, which is just a normal function, which allows you to move the object around the screen. And then I have three virtual functions: draw, resize, and rotate, because of course the way I'm going to implement this depends on the specific type of object. And this is, for example, the class circle, in which I define r as the radius and I inherit x and y as the centers. And then I'm going to, of course, have a typical constructor, and then I redefine class draw, which is a virtual function. I redefine class function resize and the function rotate. Okay, so move is a regular function, and draw, resize, and rotate are virtual functions. Okay. So this is the code, and this is the implementation of shape. Okay, I just print that move has been called, and I print the two new values of x, x, and y, y. And then let's, for example, look at triangle. Triangle derives from shape, so it includes shape because it needs to know the definition. It derives from shape, and then I define the constructor. I redefine move, and I redefine draw, resize, and rotate. And let's look at the implementation. Okay, here I have draw, resize, and rotate. Okay, so not very complex to understand. And let's look now at the main. So I define an array of 3 shapes, I initialize the 3 shapes, and I do a for cycle in which I'm going to basically print what's going on. So this trace I defined into shape.hppp. It's a macro which just prints cout executing x and lx. Okay, so basically this means that x is an expression, and this means I'm going to transform this expression into a string, and I'm going to put this string after this one. So I'm going to concatenate 2 strings, and this one instead is just the expression. So the expression is evaluated here. Okay. And so let's go back to the main, and this means basically that I'm printing executing shape draw, and then I'm calling shape draw, and the same for move, and for resize, and for rotate. Okay, now remember that draw, resize, and rotate are virtual functions, while move is not a virtual function, it's just a regular function. And remember that in shape HPP we just define move, and we provide an implementation in which we just print shape move called, and we print the 2 values. And then in triangle, for example, we redefine move to do nothing. Okay, so let's compile it now. So, and this is what is going to be printed. For example, let's look here. Shapes draw. So circle draw called, rectangle draw called, triangle draw called. Then I call move on all of them, and shape move is going to be called for all of them. And then I'm calling resize for all of them, and again the resize of every single object is going to be called, and the same for rotate. So the difference between move and draw, rotate, and resize is the fact that when I call move here, what I'm calling is the move defined inside class shape, so in the base class. So basically this means that this is looking at the type of the pointer and is calling the function defined in that type, so in the base class. Instead for draw, what happens is that the draw of every single object is called, and that means that instead of looking at the type of the pointer, I'm looking at the type of the pointed object. So this is the main difference between normal functions and the virtual functions. So how does this work? So how this dynamic binding or runtime binding works? So when you say virtual in front of a function, what happens is that actually that the C++ is going to translate the class in something a little bit different. In particular, normally a class is not so much different from a C structure. Okay, so a class is just translated into a sort of structure in memory which contains the members you define inside the class. Classes which define virtual functions are a little bit more different, because in those classes something extra is added to the structure, and in particular at the very beginning of the structure there is a specific pointer. It is a hidden pointer which is called a virtual pointer, which points to a table of functions, one for each virtual function we are going to define. Okay? Now there are many of these tables, one for each class in the hierarchy of derived classes. So you are going to have a table for class circle, which contains pointers to the member functions defined inside the circle. There is going to be another table for rectangle, which contains pointers to virtual functions defined inside rectangle, and so on and so forth. So for every class in the hierarchy here, if draw is virtual, then a table which contains a pointer to draw is going to be defined. Okay, so here we are going to have at least 3 or 4 tables, because there is also a table for shape typically. Okay, so 3 or 4 tables. Each one contains specific pointers for the different functions. Okay. Inside the object you have a pointer to one of these tables depending on the type of the object. So inside an object of type circle there will be a pointer to the table for class circle. Inside an object of type rectangle you are going to have a pointer to the table for the class rectangle, and so on. So when the compiler sees a virtual function, what it performs is this, a call to a virtual function. It performs what is called late binding or runtime binding or dynamic binding. So basically the virtual function call is translated into first get the virtual pointer, which is going to be the first element in memory for the object. You move to the right position in the table depending on which virtual function we are calling, and then you call the function. So basically calling a virtual function is a little bit different than calling a normal function. Calling a normal function is just, call the address. Calling a virtual function, you first take this pointer, you go in the table, you take the address of the function to call, and you call it. So there is one extra step. Okay, so let's do a little exercise. So please observe these two classes and the code below, and let's see which function is called at every point. So here we have two classes, class A and class B. Class B derives from A, and we have a function f defined inside class A and function f defined inside class B. And then I have a virtual void G defined inside class A and a virtual void G defined inside class B. And let's look at what they do. So function f first prints something on the screen and then it calls G. And function G simply prints something on the screen. And the same happens in the derived classes. So function f first prints bf on the screen and then calls G, and then G just prints bg. Okay? Okay. So now let's look at what is going on here. So I have P is a pointer to the base class A, and it points to an object of type B. Okay? So when I write PG, which of the two G is going to be called? I don't hear, please shout. The B1, so the second one, right? No, G is virtual. G is virtual, so dynamic binding. So this prints on the screen BG, because P is pointing to an object of type B. I do PG, G is virtual, so I look at the type of the object, which is B, and so the second one is going to be called BG. Okay? Is it clear? Yeah. Okay. Now PF, what does this print on the screen? So first of all, which F is going to be called? The first one. So first one, AF is printed on the screen. Then G is called. Which G is called? First or second? How many for the first and how many for the second? So the right answer is the second, because again G is a virtual function, and so it doesn't matter that I'm inside this function here. Okay, when I call G, it's like writing this arrow G, and this is a pointer, and so it's going to look at the actual type of object. In other words, when I call a function, a virtual function, whenever I call a virtual function through a pointer, even when I'm inside a member function like f, it always applies dynamic binding. Always. Okay? So calling a virtual function using a pointer always apply dynamic binding. So it looks at the type of the object. And this happens also when I call a function inside one other member function, for example here. So this G is actually calling the second one. Okay? So let's try to if you want, you can try it later on. Okay? I think you should try it to just make yourself convinced that this is going to work. Okay, and in the second part, I basically have the same thing. The only difference between the first part and the second part is that in the second part I'm using a reference R. But using a reference is no different than using a pointer. So RG is going to apply dynamic binding, and so it's going to call the second one. And RF is going to print the first one followed by the second one. So AF followed by BG. So the two code there are basically almost equivalent. Okay? Okay, so we just make a little break, 5 minutes break, and then we come back. Okay?